Welcome to the deep dive. This is where we take your sources and really dig into what's interesting and important.
And today, we've got quite a collection. Looks like revision notes, some really detailed diagrams, data.
Yeah, a whole stack. And it all seems to revolve around this, well, massive topic, energy and the environment.
It's huge. So what's the plan?
Our goal is to cut through all this material, figure out where energy comes from, how we actually use it.
And what it all means for the world around us. Basically, find the key stuff for you.
Exactly. Pull out those key insights. Okay, let's get into it.
What strikes me first is how the material really starts with the basics. Energy itself.
Right, not just abstract. It's like fundamental to everything. The light bulb image in the notes kind of hints at that. Powering modern life.
Absolutely. And the first big split they make, the main classification, is renewable versus non-renewable.
Yeah, that seems critical. It shapes the whole discussion, doesn't it?
Totally. So renewable sources. Think of things we can get more of, or things that just won't run out on us. Sunshine, wind, that sort of thing.
They regenerate, or there's just so much of it.
Exactly. And non-renewable.
That's the finite stuff. Once it's gone, it's gone.
No.
No do-overs.
Right. And the sources dive straight into the big non-renewables first. Fossil fuels.
Coal, oil, natural gas, the usual suspects.
And looking at those formation diagrams, wow, we're talking millions of years.
Seriously, coal, it's not just rock. It's like ancient compressed forests. Died, became peat, squeezed for ages.
Mind-blowing. And oil and gas. The diagrams show these tiny sea creatures and plants dying, sinking.
Buried under sediment on the seabed.
Yeah, and then millions of years of heat and pressure cook them into oil and gas, trapped underground. It's literally prehistoric energy.
Okay, so we know where they came from. Ancient sunlight, ancient life stored away. But how do we get from, say, a lump of coal or a gust of wind to electricity?
The generation process.
Mm.
And the notes point to a key scientific idea behind a lot of it. Electromagnetic induction.
Induction. Right, something about moving magnets and wires.
Basically, yeah. Move a conductor, like a coil of wire, through a magnetic field or move a magnet near it, and you generate an electric current. Movement into electricity.
So that's why spinning is so important. I see components like generators and turbines popping up in lots of the power plant diagrams.
Exactly. The generator does that conversion movement to electrical energy. The turbine is the bit that spins, often pushed by something.
Like steam. I see burners and boilers mentioned too, especially for the traditional methods.
Right. That leads to thermal generation. It's super common for fossil fuels and nuclear too,
So you burn the fuel or use nuclear fission.
to create intense heat. That heat boils water into high-pressure steam.
And the steam pushes the turbine.
Precisely. The steam carries the energy, spins the turbine's connected to the generator, and bingo, electricity.
Okay, let's tick through the specific methods shown in the sources. Fossil fuels, oil, coal, gas.
Classic thermal generation. Burn them, heat water, make steam, spin turbine, run generator. The coal power plant diagram lays it out perfectly.
Read Claire.
Similar end process, different heat source, uses uranium atoms. Instead of burning, you split them. That's fission. Releases enormous heat.
Which then boils water, makes steam, turns the turbine, powers the generator. Got it. Same mechanics after the heat part.
But not everything relies on steam, as you said.
Right. Geothermal. The diagram looks like it's using heat from the earth.
It is. You pump water down to naturally hot rocks. It heats up, comes back as hot water or steam.
And that turns a turbine. Or the heat is used somehow.
Often, yeah, the steam or hot water drives the turbine directly. Or the heat is used in a binary cycle to boil another liquid with a lower boiling point, and that vapor turns the turbine.
Okay. Wind power seems more straightforward.
Very mechanical. Wind blows, pushes the blades, they rotate, spin the generator. Simple concept, complex engineering.
Hydroelectric, the dam diagrams look massive. That's water power.
Yep. A dam holds back a huge amount of water in a reservoir. When you release it, gravity pulls it down through pipes.
Spinning a turbine at the bottom.
Exactly.
Yeah.
Harnessing the potential energy of the water.
Tidal power, is that similar? Using water movement?
Kind of. It uses the natural rise and fall of the tides. A barrage, like a low dam across an estuary, traps water at high tide.
Then lets it out through turbines as the tide goes down.
That's the idea. Predictable too, unlike wind.
And wave power, that sounds trickier.
It is. Capturing the energy in ocean waves, which originally comes from wind, often uses floating devices that bob up and down or move back and forth.
Activating a turbine or generator somehow.
Yeah, different designs exist. It's still a developing area compared to others.
What about solar? The diagram shows panels, not turbines.
Good catch. Yeah, solar PV photovoltaic is different. Those cells convert sunlight directly into electricity. It's called the photovoltaic effect. No moving parts like turbines.
Direct conversion. Okay. And lastly, biofuels. The notes mention burning or digestion.
Two main routes shown. You can burn biomass, wood, crops, waste, just like fossil fuels in a thermal plant, though the notes point out CO2 emissions there.
And the other way, anaerobic digestion.
Right. Using bacteria in seal tanks, no oxygen, to break down organic waste, like sewage or food scraps.
And that produces
Methane-rich biogas. You capture that gas and burn it for heat or to generate electricity. Plus, you get compost as a byproduct.
Wow, okay, so lots of ways to spin a generator, or in solar's case, bypass it entirely. But the core idea is transforming some kind of energy into electricity.
Precisely. And that variety leads us straight into the trade-offs. Every single one has pros and cons.
Yeah, the material lays these out clearly. Environmental, economic, social factors. It's complex. Let's run through them. Fossil fuels first.
Pros listed are things like, we know how to use them, the tech exists, they're convenient, relatively abundant in places, provide jobs.
But the cons, big ones. Non-renewable, they will run out. Burning them releases CO2, driving climate change. And getting them out of the ground can be environmentally damaging.
Definitely. Now, nuclear advantages.
Huge energy from a small amount of uranium. No CO2 emissions during operation, which is a major plus. The notes say abundant supply and limited waste.
But then look at the disadvantages listed for nuclear.
Right. Risk of serious accidents, think Chernobyl, Fukushima, huge health and environmental consequences. The waste is highly radioactive for centuries. That limited waste point seems optimistic, maybe?
Or perhaps it means limited volume compared to coal ash, but extremely hazardous volume. It's a point of tension in the notes.
And the cons also list limited supply, directly contradicting the abundant supply advantage mentioned earlier.
Exactly. It highlights how different sources or perspectives can frame the same issue differently. Maybe abundant now, but finite overall.
And incredibly expensive to build power plants.
Okay, moving on. Geothermal.
Pros. Renewable, no CO2. Cons. You need the right geology, specific locations, and it's expensive to set up. Renewable, no CO2. Cons. Needs windy spots dependent on weather, and some find the turbines visually intrusive. Not in my backyard sort of thing.
Renewable, no CO2 again. Cons. High initial cost to install panels, needs sunshine, so less power on cloudy days, none at night, and again, visual impact depending on the scale.
Seems like a pattern with renewables location or weather dependent.
Often, yeah. Tidal power.
Pros. Renewable, no CO2, and predictable tides are a bonus. Cons. Only works in specific coastal areas, building barrages impacts the local environment, potentially tourism, fishing.
Wave power.
Renewable, no CO2. Cons. Location dependent, potential harm to marine ecosystems and fishing, and the notes say it's often not very efficient yet. Still developing.
Hydroelectric, HEP.
Pros. Renewable, no CO2, dams can be multi-purpose, water supply, flood control. Cons. Needs suitable rivers, valleys, huge upfront costs, major environmental change, flooding large areas of land for the reservoir.
And finally, biofuels.
Pros. Renewable and growing the biofuel crops actually absorbs CO2 from the atmosphere. Cons. Burning them releases CO2 and other pollutants, and it takes up a lot of land, potentially competing with food production.
So yeah, no easy answers. Every single source has significant drawbacks alongside its benefits. It's all about balancing these trade-offs.
Which makes you think about why we need so much energy anyway, the demand side.
Exactly. The material highlights this with images, city lights, factories, transport.
Where does all that demand come from? The notes break it down.
There's industrial demand, making stuff, manufacturing. Uses a lot of energy.
Then domestic demand energy used in our homes. Heating, cooling, lights, all our gadgets. Linked to income, apparently. More money, more appliances, more energy use.
Makes sense. And transport demand. Cars, trucks, trains, planes, ships. Globalization means more goods moving around, more travel.
And bigger factors too, like the overall economy. Good times, more energy use. Bad times, less.
And climate. Colder places need more heating and lighting in winter. Hotter places need more air conditioning. Climate change itself could increase demand for cooling.
Looking at that table of coal consumption, the numbers are staggering. China, the U.S., India, millions of tons of oil equivalent.
It really drives home the scale of current energy use.
Yeah.
And how much of it is still reliant on sources like coal.
Yeah. The notes also mention energy security concepts, energy deficit, energy gap.
Basically, whether a country produces enough energy for its own needs, deficit or gap means you need to import.
Surplus means you have extra. The map shows how this varies globally.
So given the massive demand and the trade-offs in generation, what about using energy more smartly? Conservation and management.
Right, the energy conservation diagram covers this. How can we be more efficient?
First up, just using less. Reduce consumption. Simple things: turn down the heat, switch off lights, don't leave things on standby.
Also using more efficient appliances, maybe walking or cycling instead of driving short distances?
Then reduce waste. This is about stopping energy loss, mainly from buildings. Insulation is key: lofts, walls, floors, double or triple glazing.
The notes mention scrappage schemes too, getting rid of old, inefficient cars or machines.
Another angle is energy from waste. Reusing materials is one part. And that anaerobic digestion comes up again, breaking down organic waste to get biogas.
Burning household rubbish for energy, reusing cooking oil as fuel, creative ways to get value from waste.
Education is listed too, just making people aware. And government action legislation, stricter building codes, banning inefficient appliances.
And a whole raft of transport policies, things like MOT emission checks, congestion charges, fuel taxes.
Improving public transport, cycle lanes, carpooling schemes, even restricting car use on certain days in some places. Plus incentives for efficient vehicles. Lots of tools in the box.
The material also touches on R&D, looking for new ways to get energy, like fracking.
Yes, fracking. Hydraulic fracturing. The diagram shows injecting water, sand, and chemicals at high pressure.
Deep underground into shale rock to break it open.
Exactly, to fracture the rock and release trapped natural gas or oil that wouldn't flow otherwise.
It's definitely controversial. What do the sources list as the pros and cons? They seem quite balanced in the notes.
On the pro side, potentially unlocks significant new oil and gas reserves. Proponents say it's less polluting than burning coal, though it's still fossil fuel. And it can create jobs locally.
And the cons?
Big concerns about water. Risk of contaminating groundwater with the fracking fluids or escaped methane. It uses very large volumes of water.
Also potential link to minor earth tremors in some areas, and noise pollution during operation.
So another complex one with significant debate around it.
And sometimes, despite best efforts, things go wrong. The material looks at oil pollution, especially at sea.
Yeah, sobering section. Causes listed include accidents on offshore drilling rigs, explosions, platforms collapsing,
Pipeline failures, leaks, bursts.
and problems with oil tankers sinking, collisions, running aground, spilling their cargo.
The Torrey Canyon spill from 1967 is mentioned as a major historical example. The pictures are stark.
And the impacts on marine ecosystems laid out in the table are devastating.
Phytoplankton, the tiny plants at the base of the food web, die because the oil slick blocks sunlight for photosynthesis.
Fish suffer from lack of food, reduced oxygen in the water under the slick, and direct damage to their gills from the oil.
Marine mammals like seals or dolphins, they can ingest toxic oil, lose food sources, and oil mats their fur, causing them to lose insulation and potentially die from coal.
Birds are hit really hard. They swallow oil when trying to clean their feathers. The oil mats the feathers so they can't fly or stay warm, leading to drowning or freezing. Plus their food sources vanish.
Coral reefs. The notes say complete devastation, lack of oxygen, blocked sunlight. Just awful.
And beaches. Oil coats everything, kills organisms in rock pools, wipes out food sources for shore animals, and obviously ruins tourism and local fishing economies. A total mess.
So given how bad spills are, what can be done? Prevention and cleanup.
For prevention, there are international rules, like MARPOL, trying to regulate shipping and oil handling to prevent pollution.
Tanker design has improved too, right? Double hulls, separate compartments for the oil.
Yes, making them tougher and limiting the amount spilled if there is a breach. And the simplest point made: use less oil, transport less oil, fewer chances for spills. And if a spill does happen, cleanup strategies.
Several methods are listed, though often with limitations. Booms, floating barriers to try and contain the slick. But they only really work in calm seas.
Skimmers, devices that suck or wipe oil off the surface, like big floating vacuums or brushes. Again, best in calm water without too much seaweed.
Detergents or dispersants. Chemicals sprayed on the slick to break the oil into smaller droplets so it disperses in the water, but
the detergents themselves can be toxic and cause more harm sometimes.
That's the risk mentioned. It's a difficult judgment call. And for beaches, often it comes down to manual removal. People physically digging up oily sand and scraping rocks. Hard, slow work.
Wow, okay. We've covered a huge amount of ground, from like ancient forests turning into coal to harnessing the sun and wind.
Through all the different ways we generate electricity, the sheer scale of our energy needs. The pros and cons of every single option. Ways to manage energy better, new tech like fracking.
And the really grim consequences when things like oil spills happen and how we try to cope.
It really hits home how energy is connected to, well, everything. The environment, the economy, just our everyday lives.
Absolutely. It's fundamental.
So if you try and tie all this together, you've got rising demand, all these sources with their own problems, the push for renewables, the need for conservation.
It definitely leaves you with a big question to ponder.
Yeah. Thinking about everything we've unpacked from these sources, all the trade-offs, the complexities, what do you think is the single biggest challenge we face in trying to meet our energy needs sustainably?
Is it finding brand new clean sources? Is it drastically cutting how much we use? Managing the environmental damage better? Getting global agreement? Or maybe something else entirely?
Definitely something to mull over.
Thanks for joining us for this deep dive.